Hello and welcome to today's webinar from Hydromantis. We're going to be talking about dynamic parameter estimation, or the short form DPE, with real-time data today. My name is Spencer Snowling. I'm Vice President of Product Development here at Hydromantis, and I apologize for my voice today. I'm just getting over a rather significant cold. And I'm hoping my voice will be able to last throughout today's webinar as we go along. So our plan for today is to talk about what is one of the more obscure, I would say, features of GPSX, but one of the most valuable and most powerful ones in the sense that it takes our optimization feature, our optimizer tool, and provide you with a way to look at how some of those parameters that you are optimizing are going to change over time while the simulation is running. And I've put together a couple of examples today that I hope will be useful for sort of demonstrating what the value of this is, and will give you some ideas in your own mind of things that you could try with your own simulations that you're using, and then spark further ideas for us to work together in this area, moving towards the idea of having, fully online automated models that auto-calibrate themselves as new data comes along. So the plan for today is to talk about optimization in GPSX, talk about the optimizer feature that we have, just to sort of set the the basis for the discussion. Really, this is talking about using the optimizer to be able to fit to some data or to perform some other kind of optimization. Then we're going to talk about the specific form of optimization that we call dynamic parameter estimation. So looking at how things change over time during your simulation. And as I mentioned, I've put together a couple of examples that I'll run on my desktop to show you different ways in which this can be incorporated. I've tried to pick a couple of ones that I think are nice examples to show how it works, and ones that I think are sort of reasonably realistic, hopefully. And also talk about how this whole system that I'm going to show you can be incorporated with real-time data, so that as new data comes in, GPSX can handle that and can wait for new data points to become available before moving on to the next part of the optimization. And as always, if you have any questions, please feel free to type them into the questions box that's part of your GoToWebinar dashboard there. And I'll be able to see them as they come up, and our usual practice is that I will hang on and answer those questions at the end of the webinar. So I'll hang around for 5 or 10 minutes and, to do that today as usual. Excuse me. Okay, so for those of you who are familiar with GPSX, you may know that we have a tool, our optimizer tool, that can be used to do one of two things. It can be used for parameter estimation, or it can be used for process optimization, depending on which parameters that you choose to hand over control to with GPSX. The optimizer tool then takes those parameters that you've specified, and rather than being a normal slider, as you would probably have for your regular simulations, the optimizer tool, instead of having a button, the optimizer tool sets the values for each simulation that is going to run, and it runs a number of simulations one after another while trying out different values of those parameters and seeing if it can achieve the particular objective that you have specified. So it uses a search function to do this, to try and find the most optimal set of parameters to achieve the user-defined objective that you've set out for it. So the optimizer is accessed from this button here along the top of the GPSX menu bar. It's supposed to sort of look like a little graph with some data points and a line running through it. There's a button that turns things on and off, and there's a little pull-down menu next to it, which gives you access to a number of the different settings. And you can see here one of those is the type of optimization, and today we're going to be talking about DPE, dynamic parameter estimation. The optimizer tool is part of the GPSX Pro license, as is the sensitivity analyzer tool, for example. So you need to have the Pro license in order to be able to have access to these parts of the of GPSX. And as I mentioned, it can be used in two ways. you can use the optimizer to fit a model to a set of dynamic data that you have, and it will figure out what set of input parameters will fit best to that data that you have. Or you can specify a specific objective and then minimize or maximize that. So I've got some slides here to just sort of illustrate what that looks like visually. Now, this example that I'm showing you here is actually tutorial 8 in the GPSX tutorial guide, if you'd like to go through this process yourself, just to try it out. This is doing parameter estimation. This is when we have a number of data points that are measured in the field, presumably, and then we have our model prediction. And I want to be able to find out what values of these two parameters will fit the best to the set of data points that we have here. In this particular case, this is a little batch reactor where this is soluble substrate on the y-axis and time on the x-axis. And as we can see that in this little aerated bioreactor that the substrate is being used up. And we want to be able to fit the growth rate and half saturation coefficient in order to find out how that works. So you set up the optimizer, you run a number of simulations, and as you go through that process, it draws lines one after another as it goes through a number of simulations. And then eventually it converges to a final answer, and we can see here it's come up with the answers that we want, particularly for this data, and we can see here it kind of passes nicely through the data points that we have. So when you're doing parameter estimating, you are minimizing the difference between the model and the data points. Now the opposite of that, or the other option that you can do with our optimizer tool, is minimizing or maximizing some value in the model. And usually what you're trying to do is take some sort of optimization of operational parameters in the model, some measure of the performance of the model, performance of the plant. So in this particular case, this is also one of the examples that's in our sample layouts menu. If you go to the various examples that we have there, this is the alternating aeration optimization example. And what we're doing here is this is a reactor that alternates air back on and off, and we are going to optimize the cycle time. How long do we let the cycle be, and what fraction of that cycle time is aerated? So here we're saying fully aerated, but for every 3 hours we want the full 3 hours to be aerated. And that's going to get us a certain level of nitrification. Obviously not any denitrification because there's no anoxic time, and we want to use the optimizer to find out what is the optimal amount of anoxic time to have so that we can get a full, as much nitrification as possible and as much denitrification as possible. So you set up that as your objective. I'm saying here that I want to take this total nitrogen in the effluent and I want to drive that number down as low as I can. I'm doing a minimization of effluent total nitrogen. So you run that, you get that all specified up, you give it control of these two parameters, and then it starts working and it starts making some guesses. It sees which guesses are better than other guesses, and then it makes its way through and eventually it converges to a final answer here. And we can see that this answer is about as good as it's going to get. It's better than showing the 25 milligrams per liter we had there. We're down to about 17 or 16. And that's the best answer we're going to get. And here's our optimal cycle time settings that we came up with. So the objective function is the one that really sets the goal of what you are doing. So when you're fitting to the data, the objective function is to minimize the difference between the model and the data points that you have. So it takes a measurement of the error, which is basically the difference between the data point and the model, and it adds that up in some way or another. We actually have lots of different options there. You can do it as a sum of squares. You can do it as a sum of relative error and so forth, with maximum likelihood as well. As opposed to a process optimization where your objective function is a value which you're then trying to push towards 0 or to maximize as high as that you can possibly get. And therefore the optimizer chooses to find sets of parameters that will make that value as large as it possibly can. Okay, so how does it do that? Well, we use a simplex method. That is a way to be able to use a search routine where it can take the information it has from the previous run and make a better guess for the next run. It's an unconstrained optimization method, and it uses only function evaluation. So it runs the model once, and it gets a value for that objective function. It doesn't require you to be able to do derivatives. And it works pretty well for systems that are nonlinear, have discontinuities, and of course, the complex wastewater models that we do in our industry here are quite complex and do have some sort of discontinuities. If you're trying to do this with a system that has a bunch of controllers in it, a plant that has an SBR or something, there's certainly lots of discontinuous processes going on in a model like that. So a simplex is a geometrical figure in dimensions consisting of n plus 1 point. So in this case, we're talking about the number of parameters is equal to n. So if we're going to be optimizing 2 parameters, we have a 3-dimensional shape. So, oops, I've gone backwards here. Here we go. The simplex method basically evaluates the objective function at n plus 1 points to get things started, where n is the number of parameters. And then it takes a look at those guesses that it made. So if we were doing 2 parameters, it takes 3 guesses, figures out which one was the worst of those 3, and replaces that with a better guess. And it does that over and over and over again until it converges to a final answer. It's computationally intensive. It takes a lot of runs, but it is a very robust method. It allows us to capture the full results of the model. All of the information that comes from putting that model together is used in the evaluation of the objective function, and therefore you want to be able to capture all of that information. So here's a sort of a simple visual interpretation of what I was just saying before. If we had 2 parameters and we were doing an optimization, we would make 3 guesses, a starting guess, a second guess, and a third guess, and we would see which is the worst of those. And let's say, for example, the starting guess was actually the worst of those 3. We would then project between the other 2 points over to the other side and then see whether that guess was better than the one that was before. If it is, then we continue to stretch out in that direction with an expansion. We can contract back. If it's worse, we can do a number of flipping around of this, and each time looking at whatever the 3 answers that I have right now, it's going to pick the worst one and then flip through the other 2 sides and keep shrinking and expanding and keep going as you move along. This slide sort of highlights that in a nice way to be able to see it. So again, we're working with 2 parameters. This can work for any number of parameters, but for 2 of them, you can see that as that triangle, that initial guess, initial 3 guesses that we have. And let's pretend this is a surface here. This is basically a representation of the example that I showed you earlier with the half saturation constant at a maximum growth rate. And these contours are essentially the value of the objective function that we are trying to minimize. So what this is going to do is take a guess by passing through that other side and coming out and projecting onto the other side, reevaluating. It's saying, well, it's kind of downhill in this direction, so I'm going to keep going this way. And I know this is the minimum point I'm shooting for. And it keeps going until eventually it makes a guess that's actually worse than the one from before. And it knows, well, I've now passed probably the best point that I should have been. So it backs up and it starts contracting and eventually continues to contract and change direction and pass through until it gets to the final answer. And it can do this in any number of dimensions. You can put 6 parameters in there if you like, and then it can push its way through all of those. Of course, it becomes a much more sort of a longer path to get to the optimal answer when you have more parameters and more dimensions, but the simplex method does work quite well. Okay, so that's regular optimization in GPSX, and if you've seen our optimizer webinar that we did a couple of years ago, you can see more detail about that there. So now we're moving on to dynamic parameter estimation. So how is that different than a regular optimization like I just showed you? Well, the dynamic parameter estimation basically uses that same methodology, but instead of taking a single value for the entire run of that simulation, it does it in a time window that steps along. So it actually carries it out on a short little window of time, and it fits the data points that it sees during that window. And then it moves along to the next window, and it finds a new set of input parameters that are for just the data that's in the window that it sees. So it does it on a step-by-step process. So instead of getting one answer for your optimization, you would get a whole time series of answers for your optimization. So let me just take an example here, and I'm just going to run this for you live here from my desktop in a moment. This is a parameter estimation that was done for settling parameters in a primary clarifier. We can see here, if we're looking at primary effluent solids, we have some real data points, and this model has been fit as best it could be to those data points. Not a perfect fit, but it sort of does the job. But this was done with a regular optimization. This value down here at the bottom is essentially the value of the settling parameter that was done, that optimized it. We ran it, and we did that calibration. We used the optimizer tool. This is the value of the settling parameter. It gives us the absolute best fit that we can get for these data points that are shown. This is in contrast to doing the same thing with DPE. Now with DPE, we can see here that we get a time window here of about 0.25 days that shows us it's going to reset and do a new optimization for each little individual step along the way. And these values down here change over time. So this is where the real value of DPE comes in, because not only are you getting a nicely fit model, you're getting it fit to the data quite nicely and getting some good predictions there, but what you're also getting is a time series and input. What was required to be able to fit this? And you'll notice here at the front end, by the way, that the DPE fit is quite a little bit better, particularly on these data points right here, because we allowed the model to change that value of the settling parameter that it was trying to find, that it was trying to optimize. We allowed it to change for that little portion of the simulation before going back to pretty much the value it had before. This is indicating that there was some sort of settling issue happening there, and there was the settling parameter of the model was not really constant over the length of that simulation. Something was going on here that is reflected in the data, but the model can't fit to it unless we allow it to change and then go back to the value that it came from before. So this is telling us a little story here about what was going on in the model. So that leaves us with the question of why is this useful? So what is the advantage of this over regular simulation, regular optimization? Well, again, I guess I sort of summarized it at the end of that previous slide there. DPE allows us to sort of not look at just one value for the entire simulation, but rather a time series of values. And quite often that time series of input parameters can tell you a story about what's going on during that simulation. One value didn't cut it throughout the whole length of that simulation. You can get a better fit by allowing some of those things that would normally be constant during your run to vary with time. And if the model says, well, I'm using my DPE here, and the model is trying to tell me that I really need to push down my oxygen transfer efficiency, or I really need to bump up these settling parameters in order to fit that data, well then obviously that's a nice way to pull some information out of your model that you may not have otherwise been able to see. It's really good for picking out things where there's sort of a constant trend in an input value. You may find that something is dipping over time during that simulation. It's therefore that input parameter that you're holding constant maybe really isn't constant. You can use it where you can suddenly see a change in one of those input parameters. In order to fit that data, suddenly that input parameter had to change from one value to another. Clearly there's something going on there in the data, but you need the DPE optimization to be able to pull it out and see it. And it's also good, too, to sort of evaluate the data that you have. Sometimes you may find that it's not an issue so much of the process it's just of closing the loop on your mass balance, for example, maybe. And so if you have some data where there's a sensor drift or a calibration on one of those sensors going out or drifting over time, you may be able to pick that out and be able to pull that out and kind of see that over time with your DPE optimization. Okay, so excuse me. I would like to run my usual types of desktop demonstrations that I have going here. So just give me one moment to have a drink of water here. Okay, so far the voice is surviving. Okay, so what I'm going to show you here is pretty much tutorial 10. If you would like to go and go through the GPSX tutorials, you can always pop up here to our sample layouts menu, go to the tutorials, jump on to tutorial 10. This is what I'm showing you here with a couple of minor modifications just to make it run a little smoother. So what we're looking at here is an influent coming into this primary clarifier, and we are going to be optimizing the value of the settling parameters so that we can get a good fit to some dynamic performance of effluent primary solids. So we can see here, first of all, looking at the way that this is set up, we can see that we're reading quite a bit of information about the influent here. So this is a lot of dynamics going on. The BOD and solids and TKN coming into that tank are changing over time. The flow is changing over time. Here's the influent flow that's going to be changing while we're running that simulation. The underflow rate is also changing. So there's a lot of dynamics happening there, but we want to be able to fit that primary effluent data that we have. So I'm going to run it once without any optimization turning on, just so that you can see here, if I hold my settling parameter the same, a constant value, well, it's not a super spectacular fit over here. We can probably improve upon that by doing a better job of fitting this data up here in the corner, primary effluent solids, by allowing GPSX to find us a better value of the settling parameter. And again, we're not going to do it just one value for that entire run. We're going to let it do it in that piecewise, stepwise manner. So the way I do that is I come up here, I select DPE. Actually, it's already been selected for us. And I'm going to turn on the optimizer. And then I'm going to hit start again. And we'll see here, and I hope you can pick this up well enough, it's doing this a little bit at a time. And you can see some consecutive guesses, some really bad ones, and then eventually it converges to an answer before it moves on to the next time window. And in each case, down here at the bottom, you can see that it's making consecutive guesses of what these settling parameters are supposed to be. I'm going to run that one more time just so you have a chance to see that. As these guesses improve, it's converging to a new value of the settling parameter. Here we can see that each of one of these little windows that we are running, it's getting a new value for that settling parameter. We can see how that changes over time as the simulation went along, and we got a much better fit here. And this is the same simulation that I was showing you on those slides earlier. So it's kind of like doing optimizations one after another over time, only looking at the data that's within each window, and it uses the end of the previous window as the beginning of the next window in terms of initial conditions for the simulation. Okay, so that's primary effluent solids. I'm going to actually, I made up another example here, which I'm going to show you. And well, this is to deal with trying to use DPE to pick out some information about what's going on with this aeration in this completely mixed activated sludge tank here. So just very quickly, this is some primary effluent coming into a CSTR in a conventional activated sludge tank. And in this particular simulation here, for the beginning of what I'm going to do here, I'm going to keep everything constant in terms of its influent, in terms of the loading and so on, just so that you can sort of see what's going on with the demonstration and with the activity of the search routine. And then we'll move on to a more realistic example of the same thing. Okay, so in that bioreactor, right now we have diffused air, and there's lots of air being supplied. But we don't have any DO controller on. And the one thing that I'm going to be playing around with here is the fouling constant. Now, just so that you're familiar with what the fouling constant is in GPSX, if you haven't ever played around with it, it's a value that is a default of 1.0 that we multiply the oxygen mass transfer coefficient by during the calculations to go from airflow to KLA. And so in this particular case, when you have a 1.0 fouling constant, that means there's no fouling at all, it's perfectly clean. As you get a more fouled situation, as time goes on, a fouling constant would become a lower number. You would move down to 0.6 and 0.2 and so on. I guess you never get down that low, 0.2, but from 1.0, it's faded down to 0.7 or something like that. So these are all values that would indicate that a lower value of the fouling constant would indicate a more fouled situation. You're probably pushing a bit more air through there just to be able to get the same amount of oxygen transfer. Okay, so first of all, what I'm going to do is I'm going to turn the DPE on here. Let's go to DPE. Oops, there it is. I'm going to turn on that simulation, and we are going to be looking at dissolved oxygen here. We're going to be looking at effluent ammonia and effluent soluble BOD5. So these are the three things that we're trying to fit the model to. It's going to be looking through all three of these variables here in order to find out, to fit to the data points that are shown. Okay, so I'm going to run that. It's going to display the data points, and it's going to start the optimization. And we can see here that it's guessing at the very beginning that the fouling constant is still pretty close to 1. And we can see that it's fitting this data and this data down here pretty well. You can see, obviously, that this is an example. As I said, I'm doing this in a very simple way so that you can see the activity here as this is coming along. And I created this data by moving the fouling factor on my own. What I'm going to do now is I'm going to compare this DPE result with the data points that I actually used and see if it can back out the correct value in order to get to where we want to be. And I've actually plotted that over here. So this is almost done here as we're moving through these last few time window steps. And we can see now what it's showing is now it started out at 1, but it started getting to the point here where it's down around 0.7. And if we look over here, these data points are the ones that I actually used to generate that data with, and we can see that the lines, which are the ones from the model backed out, well, not perfectly every time, but backed out a pretty consistent set of pretty good guesses about what values of fouling that I used to be able to fit that data, to create the data that it was fitting to. Okay, so that's not very realistic, but at least shows you what's going on. Okay, so now I'm going to go to a much more interesting example, which is to do a dynamic influence. Okay, so I'm going to run this once just to show you exactly what's going on here. So now you'll note that I'm now changing the influent flow, the influent COD, the influent TKN. The loading is going to change as the simulation is running. And again, we have data for effluent BOD5, we have data for effluent ammonia and for DO. And we're going to be fitting to that as well. So let me run that now. And you'll see here that our effluent ammonia data points show that there's not much really changed in the effluent, and the BOD was pretty flat as we go along. The DO actually kind of goes up and down a few times. And what the model is showing us here is as it's trying to fit with these sort of complicated loading changes that are going on throughout the length of the simulation, is that the fouling constant is changing over time, but it's not nearly as obvious a case now as it was before. The DO is going up and down, the effluent is pretty much staying the same, so it's not obvious to me what the fouling factor should be in order to fit those. And that's really where the value of DPE comes in. It can run these simulations over and over again using that search routine to find the correct value of the fouling in order to match this and this and this all together, despite the fact that the loading is changing all the way through this. So it's kind of a really excellent way to sort of highlight the value of DPE here, because we're taking a situation where the information about whether DO is going up or down, is it due to the loading change or is it due to the fact that there's some fouling going on? We don't really know because those two things are mixed together. Well, we can back out what the fouling constant is in order to be able to match to that data that was coming in. So we can see here that this fouling is actually going down over time. And again, that's sort of a typical of what you would get in a simulation where there's some fouling building up over time while the simulation is running. And it's only these set of fouling parameters that would actually fit all three of these parameters here at the same time. So this is kind of a helpful way to sort of evaluate your data when you think that maybe something is going on you can't seem to capture for at least the entire run one value of something that would work. Like I can't find one value of KLA that will give me, or one value of oxygen transfer efficiency that will work for all of the data points in my run. Well, maybe that is because it actually isn't one value. It's something that's going to go up and down over time. And if you apply the DPE, it can actually do that parameter estimation for you and find out what the trend looks like during that simulation in order to fit these data that you actually do have. Okay, so let's come back to the slides here. Now we'll get to the last point is, okay, so how does all of this work with real-time data? So everything I've showed you here before is working under the assumption that you have a time series of data, input values, effluent values, other DO values, something that is a time series that you can fit to. But in the case of doing it with real-time data, GPSX actually has some tools built in that can continually check for when new data becomes available. So what it does is you specify a certain number of files that you would like it to monitor. Those are the ones that are going to be updated when new data comes available from the plant via SCADA system or whatever data collection system that you are using. And when it sees that there is sufficient data, usually you would want to wait until there's at least a few new data points to be able to move ahead, and it sees that it's got some new, the DPE optimizers sees that there's some new data to work with, it then goes ahead and does the next time window. And what you get out of that is a completely up-to-date real-time version of that settling parameter or that fouling parameter or your oxygen transfer efficiency number. Whatever it is that you feel is the thing that you want to be able to extract in real time out of the data that you have. You have the model running all the time. Every time new data comes in, GPSX comes to life, does an auto-calibration, finds that new value of that parameter, and you know that that's now the new value for real time as it was in this most recent window of data. Now, it takes a little bit of effort to set this up and get it working the way that you need. There's a lot of data checking and synchronizing with the files, and a lot of that information is available in the GPSX online menu, which is in the input parameters menu from the general data system menu. And it looks like this. You'll have to turn on an online run, and you have to specify some data about how frequently you want GPSX to check that file and how many data points should it wait for before it starts up with the new DPE run. And you kind of sync that up with the time, the DPE time window that you want to work from. And there's a lot of other details about reading the information in there. Now, it wouldn't be very exciting for me to run that for you right now live in this webinar, because watching things happen in real time is really slow in the wastewater world. So rather than showing you something really slowly happening, I've sort of mimicked it on this slide to show you what happens. So normally when you would get everything set up and you'd get the model up and running and you'd start to collect the first few data points, nothing would be happening with the simulation until it saw enough data points that it felt worthwhile to take that first parameter estimation. So it would then start the parameter estimation process and go through those iterations like you've seen on the demonstrations I just ran. And then it would come to a conclusion. Here's your new value of the parameter that we were optimizing, and then it stops. And now it waits for new data points to arrive. And eventually enough of those will happen, and it'll plot them along until it sees that it's got enough in that window, and then it performs the next step for doing the optimization, and then it waits for more data points, and then does another optimization. It just continues to do this for as long as you want it to run. What this gives you is a real-time parameter estimation from that real online plant data, and it does it in this little time step of a window. What you end up getting out of that is slowly, one step at a time, a value that you get out of your model. So you'll slowly get, for example, fouling constants for your aeration calculations that come out of that. And you can just come back here and look and find out, well, which is the fouling constant for today. You know, and you can look to see whether there's going to be some trends that change over time, except you can now get this on a real-time, up-to-date basis. Okay, a few final thoughts on that. DPE is certainly one of the most advanced features in GPSX. It's combining, you know, real-time data transfer and optimization and the best parts of parameter estimation all together into one little tool. It's very good for systems where you would like to be able to know how fast one of my input parameters is changing, but I can't measure it directly, so I kind of have to back it out from some other measurements that I can take. So I don't really know exactly, you know, what my transfer efficiency is, but I can sort of back it out by looking at airflow and DO and, you know, oxygen uptake rate and a few other things. I could take those data, feed it into the model, back out what my transfer efficiency is, and then see how that changes over time. And you can do that. That's really sort of creating a soft sensor by creating, you know, doing this sort of real-time parameter estimation as it comes along. So as I mentioned, It's a little bit of a finicky thing to set up. You have to have a pretty good model already put together and nicely calibrated in place, because of course you can't change all of the parameters. You only want to do the ones that are specifically of interest to you, and you got to be able to read in all of the influent loading and all of that other stuff too. And we have experience doing this, and it's one of our most advanced things that we do. And if you would like to know more about it, you can contact us for more details.